All right, let's get started. 3 minutes early. Okay, so the next topic today is immunoassays. So we're getting close to being done here. After immunoassays, we have chemical contaminants of concerns. And some of those chemical contaminants of concern are analyzed using immunoassays. So that's why we want to talk about immunoassays today before chemical contaminants of concern. All right. So what does immunoassay involve? What does the assay involve? Come on, stay alive, keep up. It's like only 2 more lectures of food analysis. Immunoassays. What do you use in these assays? What do you rely on in these assays? No? Nothing? Well, antibodies. We rely on antibodies. So we use antibodies as tools to determine the presence of what we call as antigen. And the antigen can be in many different types of compounds. Okay, so antibodies. So immunoassays rely on antibody binding to the antigen. Antigen is a foreign object or body that is introduced and induces the production of antibodies and then potentially immunoreactivity, depending on if that's going to be an allergic component or not. But for us, we don't care about that. We care about using antibody that would detect the presence of an antigen. The antibodies are proteins, so this isn't one antibody, but it has 4 different polypeptide chains, 2 heavy chains that are identical, and 2 light chains that are also identical. Okay? And this region here is the binding region for the binding with the antigen. Okay, so there are identical binding sites. So antigens that are identical can bind on both sides on one antibody. Okay? And they're produced in the cell by B cells, specifically B cells, upon the introduction of a foreign body. So the interaction is very, very specific and very, very strong. It's the strongest non-covalent interaction that can happen. Okay? So the affinity is huge between the antibody and its antigen. And like I said, it's the strongest non-covalent. So there's no covalent linkages. It's non-covalent, could be hydrogen bond, ionic, hydrophobic, van der Waals. Very specific and very strong with really high affinity constant. All right, so things that you need to know are what we call an epitope. An epitope is the region on the antigen that binds to the antibody. So if we have a protein, let's say, so you have a protein which is a really big molecule, and then you inject this protein in the bloodstream of an animal. The animal is going to produce antibodies, but the antibodies will be specific to certain regions on the protein. Okay? And then the antibodies can bind to that region. Okay? Every region is called an epitope. So the region on the protein that binds to the antibody via very specific interactions is called an epitope. Okay? So if it's a protein, sometimes the epitope is linear. That means amino acids are in linear form that form an epitope where an antibody binds. protein bends and have a certain conformation, the amino acids that form an epitope are non-linear. That means they're not in sequence with each other. So you have 1, 2, 3 here, and in another region you have 4, 5. So this forms conformational epitope. Okay, so we have linear epitope and conformation epitope. Okay. So the size of that epitope is equivalent to 7 glucose units or 1 kilodalton. 1,000 grams or 1 kilodalton per mole. So another important aspect that I want you to know is that antibodies can be polyclonal or monoclonal. Okay, let's say you injected this protein in an animal, a rabbit, a sheep, a goat, whatever, and then the B cells in the animals, there are several different types of B cells, will produce antibodies that can recognize different epitope. So this antibody is different than this, is different than this, is different and different, because they recognize different epitopes. This is called polyclonal. Okay? That means you generated antibodies that recognize different epitopes. Monoclonal antibodies are very important for immunoassay kit. That you go and purchase a kit, it will be really helpful for an immunoassay to have monoclonal antibodies. That means all of the antibodies will recognize one type of epitope. So monoclonal, that means the same antibody will recognize the same epitope. That's very convenient for assays, kits that you would purchase. How do we form monoclonal? Can you say that 10 times in a row? Monoclonal. Okay, so how can we produce that? Actually, it's been produced by linking a B cell, one type of B cell, to a carcinogenic, not carcinogenic, the cells that multiply, cancer cells. So cancer cells can multiply very rapidly, so they fuse the B cell to cancer cells, so they can multiply the B cells as well very rapidly and produce large amount of the same B cell that can produce the same antibody, a monoclonal antibody. Okay, so polyclonal, monoclonal, that will be helpful for you to know when we're talking about different assays. So immunoassays are specific, sensitive, and simple. Perfect. Okay? So specific, we know that by definition, specificity means targets one type of analyte, so it has a specificity to a certain antigen. Sensitive, we have low thresholds, so we can determine differences, minute differences between samples, and simple to follow. Many times it's a kit that you purchase, other times it's reagents that you can actually put together easily and run the assay. So we do have to find appropriate antibodies for the antigen of interest. Sometimes these are the monoclonal that we can buy. Other times we actually use, for example, for allergy testing, we use sera from people that are allergic. So we get blood and separate the blood into extract the sera and use the sera as a source of antibodies to detect changes in allergens due to processing, for example. But we need to get the appropriate antibody for what we're looking for. So the assay, we should be able to separate and differentiate bound antigen from not bound antigen, and then I will show you that in a minute. How can we differentiate and separate between an antigen that is bound versus an antigen that is not bound? So the common feature that we use in immunoassay is the fact that proteins have hydrophobicity on the surface and they can bind to hydrophobic regions. So that feature is very important in setting the assay. So how do we produce antibodies specific for measuring the target antigen? We said that either we inject an animal with the antigen of interest and collect the blood and generate the antibodies from the serum, or we get our monoclonal antibodies that could be purchased. All right, so what are some applications for immunoassays? Yes, Laura. Determining allergenicity, yes. So oftentimes we look at products or ingredients and look at how certain processing can impact allergenicity. So we need to use these assays. Okay, what else have you heard that immunoassays are used for? Random. Hayden.
I heard one time they're trying to develop immunoassays for prions. Is that like prions is food or something like that?
Is that like toxic compounds?
Yeah.
Yes, yes. Yes, Laura?
Isn't it also to diagnose HIV?
Yes, so it's used for viruses and also microbial detection, bacterial and viruses detection. And it is used for toxins in food. It could be pesticides, mycotoxin. We will learn about those next. So it has multiple applications. So allergens is a big one. Gene species authentication. A few years ago, there was this something that came up in the news that beef patties are made with some horse meat. So you can actually extract the proteins from the meat patty and run an immunoassay to determine the authenticity. Do you have beef? Do you have pork? Do you have horse? What do you have in there? Genetic modification genetically modified organisms can also be detected by immunoassays. Toxins, there are many of them. And then also identification of bacteria and viruses. So a lot of application for immunoassays. Okay, so now in terms of analytical techniques, the most common analytical technique is ELISA. And I'm sure many of you heard of it. It stands for enzyme-linked immunosorbent assay. We use enzymes for detection, okay, so that we can convert the product into the substrate into a product that has is a chromophore, so you can measure absorption. Okay, so it is ELISA, and we have sandwich ELISA, which we will talk about, comparative ELISA, and indirect ELISA. These are the most common ELISAs that are used. And then we have other immuno-based analytical techniques like the immunoaffinity chromatography, where you use it to purify antibodies or to purify antigens. Lateral flow strips, we will talk about that in a minute. It applies actually a sandwich ELISA concept. And then Western blot is a qualitative means of an immunoassay. Okay. So in an enzyme-linked assay or ELISA, what you have are specific enzymes that are fast-acting. The most common ones that are used are horseradish peroxidase and alkaline phosphatase. They are very stable enzymes and very fast-acting. They can convert products to substrate very quickly. And in an assay, you want something that works fast. They can be easily linked to the antibody, attached to the antibody, or easily attached to the antigen. And like I said, they're quick in converting substrate to products. And the product produced are chromophores, so we can use them to detect or measure. And we often use an ELISA plate reader, which is very convenient. And here it is. So you have a plate that has 96 wells, and you can run many samples. You can run your standards, you can run your samples, different dilutions, and then you can put that entire slate in a plate reader instead of having your sample in a cuvette. So each well can take about 300 microliters of sample. So you can fill them all, put them in, few seconds, get a reading. So it's very, very convenient. So you can read 96 samples in one shot instead of having what do you call it, cuvette, changing it 96 times. So the main steps of an ELISA, I'm going to picture here a sandwich ELISA to explain the main steps. This is a very common college board question if you are in college board. Okay, so what happens here is you have a surface, and oftentimes your surface is the one well in the microplate that you use. So you have the surface and it's hydrophobic. Surface. So your antibody, first we're going to put antibody. We can put antigen first, or we can put a solution of antibodies first. So your antibodies are proteins. So they're going to bind to the surface, attach themselves to the surface via hydrophobic interactions. Then now I'm going to introduce something that we call will block the regions, because you don't want any non-specific interaction. So first you bound your antibody, second you would add a protein, and usually it's bovine serum albumin or gelatin or any protein that you don't care for in your assay, so that you block all the rest of the surface, because you don't want your antigen to bind non-specifically to the surface. You want it to bind, if it's present, you want it to bind to your antibody. So the first step then is immunoassays, second step is a blocking agent, then you do a wash. You wash so that anything not bound will be washed off, because all you need is the stuff that are bound. So every time you add a reagent, you do a wash step. Then you introduce your sample. So your sample has your antigen, has different types in there. So your antigen is going to bind. Everything else, wash. So anything else that doesn't bind will be washed. Then after that, you can put another antibody that will recognize the antigen, but that antibody is labeled with the enzyme, is linked to the enzyme. So you add that, and then you wash, another wash, and then finally you add your substrate. When you add your substrate, the substrate will react with the enzyme, gives you product, and you measure absorption. There you go. So every time you have a step, you incubate, you wash, you add your second reagent, you wash, and so on until you finally get a product that you can read using a spectrophotometer. And this is the sandwich ELISA. I might give you a figure on the final and tell you to label it. Okay, so you really need to know the different parts. Okay, so you have the solid phase, which is the hydrophobic phase. You have the capture antibody. That means the antibody that will capture the antigen. This is capture antibody. Then this is your antigen or analyte that is of interest. And then the sample components that you care for will be washed off. And then you would have another antibody that is labeled. We call it detection antibody. So now these are the things you need to know. The solid phase, hydrophobic phase, capture antibody, your antigen from your sample, your detection antibody that is labeled with the enzyme, your substrate that will bind to the enzyme and produce the product that is what you would measure the absorption on. Okay, so that's the sandwich ELISA. It's called sandwich ELISA because the antibodies are sandwiching your antigen. Hence the name sandwich ELISA. Now, in reality, most of your ELISA or sandwich ELISA are indirect. Indirect sandwich ELISA. So Going back once, this is direct ELISA. You have your detection antibody that will sandwich it is the one that is labeled. Now, in the indirect, all the steps are the same except the antibody here, we call it primary antibody, this one over here, the one that will sandwich your antigen, but it's not labeled. And oftentimes when we're using sera from a human sera to determine allergenicity, for example, we're not going to label that sera and antibody. It's a lengthy process. What we would do is we purchase a secondary antibody that is labeled already for us. So this is very convenient that we would do that. So what kind of antibody we purchase is an antibody to the antibody. Getting complex. So this antibody, assuming it's a human antibody that we use in our assay to determine allergenicity, this one over here, then what we want is antibody to the human antibody. So what we do is we get a goat, we inject human antibody in their bloodstream, and they will form antibodies for the human antibody. We collect that, we label that, and then we sell it as a pre-labeled antibody for a human antibody. And that's what we call a secondary antibody. Primary, that captures the antigen or sandwiches the antigen. So you have the capture antibody, the primary antibody that sandwiches it, and the antibody to the antibody that is already labeled with the enzyme for us that we can purchase. And then we add our substrate and then convert that to product. This is the most common sandwich ELISA, is the indirect. Just because the availability of an antibody that is already labeled will make it easier for us when we do the analysis. Any questions? All right. These are recap questions for you guys to study from. Moving on to competitive ELISA. So the competitive ELISA is designed for smallish molecules, not for proteins. That means for molecules that are less than 5 kilodalton. So they cannot be sandwiched. The whole molecule can be one epitope. So if you have a molecule that has one epitope, it will bind to this antibody, but it can't bind to any other antibody because the whole molecule is the epitope. In this case, they designed what is called competitive ELISA for small molecular weight. So for mycotoxins, other toxins, pesticides, anything small in molecular weight can be run by competitive ELISA. So what we do usually to get antibodies for these toxins or small molecules is we link that molecule to a protein that we don't care for. Could be albumin protein. So albumin protein from whey or albumin protein from eggs. It can be a carrier protein. So the carrier protein is linked to our antigen and is injected into the animal to produce epitopes. To produce antibodies for this small molecule. So then what happens is we have the same setup. So we have our hydrophobic surface, and then we have, it's up there, we'll start here, hydrophobic surface, your antibodies, and then your antigen, if it's present, it will bind to one of the antibodies. So what will you do? You cannot bind an enzyme, you cannot do anything, it's a small molecule. In this case, you introduce a similar compound that is bound to an enzyme. Up there, I don't know if you can see where I'm pointing. Here, up here. So you have your same molecule bound to an enzyme. So you have the molecule that is in your sample, and then you have the molecule bound to enzyme that you're going to introduce in the assay. So what's going to happen is competition, hence the name competitive ELISA. So both are going to compete for sites on the antibodies. If we have a lot of toxin in our sample, they will compete more and bind to more sites, so we have less enzyme bound. So will the absorption be higher or lower if you have more toxins? If you have more toxins, less antigen bound to an enzyme will be linked to your antibody. So when you put the substrate, there's not going to be a lot of enzyme because the sample that you have has the toxin and is not labeled, so it's going to take the spot and prevent the labeled one to bind. Okay? So if you don't have the labeled one bound, then you don't have that enzyme. When you wash, the enzyme will be washed off because it's not bound. Then you will have lower absorption. Okay? So usually you run your blank where you don't have a sample. So you run the blank, and the blank will have no antigen, and then when you add your antigen that is bound to the enzyme, you have the highest absorption. Okay? So in competitive ELISA, high absorption means low amount of antigen in your sample. Whereas regular ELISA, whether it's sandwich or indirect ELISA, high absorption means high amount of antigen. In this case, in competitive ELISA, it's the opposite. The more is the absorption, the less the presence of antigen. Because this means you have less of it in the sample, the labeled one has room to bind, whereas the non-labeled one that is in low concentration will not compete as much. And this is another illustration. So here in this case, bound antibody. So we have our hydrophobic surface, we have our antibodies bound to it, and then we have the antigen and the hapten that has the antigen that is labeled. So if I have less of my antigen in the sample, more of the labeled one will be bound. Okay? That means higher absorption. You can do it where you bind the hapten, which is the carrier protein and the antigen, and then you label the antibody with the enzyme. Monoclonal antibody labeled with enzyme. Okay, so you have that. So if you have the antigen in your sample, it will bind. If you don't have it, then your antibody that is labeled will be bound, and then you have higher absorption. This is, for example, aflatoxin detection. So if you have aflatoxin in your sample at high amount, then you have low absorption, that's high toxin. If you don't have as much, all of the labeled ones will be bound, and then you have the maximum absorption, that means no toxin. Okay. So we can use chromatography, like I said, to purify antigens using antibodies on your stationary phase. This guy always passes by around this time. Or you can use antigen instead on your stationary phase and isolate antibodies for analysis. Okay. So this is the lateral flow strip, which is a qualitative assay determining the presence or absence. This is used quite a bit on the field. Let's say you are screening a field that they're claiming there's no GMO, no genetic modification. You can go get a sample and quickly get an extract from the sample and dip your strip in it to see whether or not that GMO protein is there or not. So this is done on the field, this quick method. Another example for its use that is not related to food science is your typical pregnancy test. which you might be introduced to later on in life. So what happens here, and the yellow color is incidental, it's not anything. But, so what happens here on the strip, you have antibodies that are labeled with a color, with a blue color, here on that strip. When you dip it in your solution, if you have that protein of interest, it will bind to the antibody, and by lateral flow, they're going to move up to another location where the antibody specific to that protein is immobilized. So then this antibody that is labeled carrying an antigen will reach and then form a sandwich. This is a sandwich ELISA based on. And then you see a blue line developed. The test line, the blue line developed. Now in every test strip there is a control line to know that the strip works, that it's actually not flawed or anything. So what happens is your antibodies that are labeled blue, they're going to move up the stream no matter what, whether they're carrying an antigen or not, they're going to move up. If they're carrying an antigen, they're going to be blocked at the test line, where they're going to capture that antigen and stay there, and you see it go. If they're not carrying an antigen, all the remaining that are not carrying an antigen will continue to go up to the test, to the control line, where you have an antibody to the antibody that is carrying the blue color. So we always see that line. So this is the negative control, this is the test. So you always see that to ensure that the antibodies here are actually functioning and moving up when you insert your sample in an aqueous solution. So they're going to move up and be captured by the antibody to the antibody that is labeled. However, again, if you have the antigen, you will see two lines. One where you have an antibody to the antigen, and then one that is, again, the antibody to the antibody carrying the blue line, or the blue color. Okay. So the last immunoassay here is Western blot. In Western blot, you start with gel. You run a first dimension gel and a second dimension gel, so you end up with a gel where you have spots of your proteins. For instance, let's say you're looking for proteins from different sources, horse versus pork versus beef. So you can run your mixture of proteins and they get separated by two-dimensional electrophoresis. Then we blot them, we transfer them. Usually I bring my tool here and I forgot today. We transfer them into a PVDF membrane that is durable. It has a hydrophobic surface, so once you apply a current, they're going to move in certain direction and the spots are transferred onto a durable hydrophobic surface. We call it polyvinylidene difluoride membrane, PVDF membrane. So now you have your proteins here, and then you incubate, you block everything else with bovine-serum albumin or whatever, so that you don't have non-specific binding. And then you wash, and then you add your antibody. If you have the antigen here, the antibody is going to bind to it. Then you add your secondary antibody, which is labeled by an enzyme. And the secondary antibody is the antibody to this antibody. And then you wash, you add your substrate, you get product. And then you see, if your antigen is there, you see a spot at that location, a colored spot at that location. And this is an example. In this case, it's a one-dimensional gel, and you're looking at a specific protein and for pork, and then you incubate with antigen specific, antibody specific to that, and then after you transfer and blot and everything, you see only that one spot that reacted to that one specific antigen. Okay, great. I'm going to move to the next topic. Analysis of contaminants or food contaminants, residues, and chemical constituents of concern. This is a whole list, a very long list of contaminants of concern. So this is kind of a representation of the chain or the circle that the food goes through to get to us as consumers. So it starts with the farming, whether it's animals or crops, and then it goes to the processing, and from processing to retail, transportation, storage, and then there's storage here, and then consumers. Can you think of contaminants that can happen at any point here that could be of concern? Hayden, what do you think?
Well, farmers and animals, you can get any type of bacterial contamination, such as
Yeah, so yes, so microbial is a big one, definitely. At any time and location during transport, storage, yeah, microbial contamination. But let's not talk about microbes.
Sorry, aflatoxin.
Oh, yes, exactly. So if you have growth of fungus, fungal growth or mold growth anywhere while in the production of the produce during storage, during transportation, due to temperature and humidity, you might get molds, and then you can get mycotoxins and aflatoxins and stuff like that. What else can you think of? Yes, April?
Cross-contamination of like allergens.
Cross-contaminations of allergens, yes, can happen during transportation, during processing, and, well, if you didn't do good labeling, yes, it might wind up to the consumers. Other than that, yes. Huh?
Metal fragments.
Yes, metal fragments, glass fragments, yes, definitely can get in that process. What else? What do you usually feed to animals if they have an infection? Antibiotics. We don't want antibiotics to wind up in our milk or meat or any of that. So antibiotics. What else can wind up? Have you heard of a case that actually was intentional contamination for economic benefit? It happened a few years ago, huh? Melamine. So melamine is a compound that is high in nitrogen. So they wanted to fakely increase the amount of protein in the sample. By adding this melamine, it's detected as protein. So melamine can cause problems to the kidneys, and sometimes it's fatal, depending on the concentration. So intentional adulteration. Let's see. So pesticides is another one. So allergens, mycotoxins, pesticides. Presence of adulteration, presence of other substances like sulfites that people can be sensitive to. So, many of these outbreaks or hazard reports are due to chemical. Chemical can be pesticides or heavy metal or sulfites or allergens. Mycotoxins from mold and fungal growth, microbial is a big one. And then others, the fraud, biological hazards, labeling, use certain packaging that has like bisphenol A, for example, or some ink material that can get into the food and be hazardous. There's so many of them. So the main ones are pesticides, drug residues like antibiotics, mycotoxins, allergens. So for pesticides, drug residues, and mycotoxins, there's governmental tolerance level. Tolerance level for antibiotic is 0, for example. For pesticides, depending on the pesticide, there are different tolerance levels. Depending on the mycotoxin, some mycotoxin tolerance level is 0, like aflatoxin B, for example. So there's no tolerance level for it, 0. So chemical additives, adulteration that is intentional, melamine, food additives like sulfite, Nitrite. Nitrite in meat can react with protein, gives you nitrosamines. So many. We're going to talk about so many. All right. So this is a summary table that I would like you to use and to study from. It gives you a breakdown of the contaminant, what kind of quantitative assays, and what semi-quantitative or qualitative assays. So we'll be covering a lot of these examples, but here is a nice summary to study from. So pesticides, we have the multi-residue method. That means you're measuring in one extraction and one analysis multiple pesticides that could be present in your sample. However, you can do the single residue assay where you extract uniquely for one pesticide and then determine its quantity. And this is mostly used, the single residue is mostly used when you are determining the tolerance levels and determining the toxicity of that pesticide. And then most of the methods you can see are like chromatography methods. Pesticides, it's mostly GC, but some of the new pesticides that are coming out are polar, non-volatile, so we're using HPLC for those. And then thin layer chromatography, enzyme inhibition, and immunoassays are your semi-quantitative method, and we'll give examples as well. So you'll see also mycotoxins, you have chromatography, most HPLC because they are on the polar side, non-volatile. Antibiotics, the GMO is mostly with either DNA methods, PCR or ELISA, to detect proteins of GMO. Lateral flow strip is our semi-quantitative one for allergen as well, similar. Allergens, you can use LCMS as well. And sulfide, we have a bunch of methods that we will talk about, and nitrites as well. Okay, so this is a good summary for you to study from. So when we're determining contaminants of concern, most of the time they are not present equally distributed in your sample. So it's very, very important that you homogenize. For example, mycotoxin, you might have a mold growth in one region and none in another. So when we collect the sample for testing, it has to be homogeneous and it has to be representative of the entire population. So you want to remember your chapter 5 in this case. Your representative sampling, the sampling that makes sure that you did not miss anything because this would cause high risk on consumers. And then the sample must be completely homogenized before you start your analysis. Okay? So we collect the sample, we homogenize the sample, and then we prepare it for analysis. Oftentimes we extract with a solvent. We really need to know the characteristic of the component we are searching for. What is the pesticide we're searching for? What its molecular and chemical characteristics. Then we choose an extraction solvent. And then we purify, clean up by removing residues, concentrate, and if we need to use GC, we need to derivatize. We separate, and then we analyze, and then we quantitate, and then we report. That's your general procedure. The method of choice, it really depends on the food matrix, how complex, what do we know about the analyte, and can we perform this assay or not, and are we looking for multi-residue or single residue? When you're looking for single residue, it will be very, very specific method. So this is kind of like a more detail on the sample preparation and extraction, filtration, clean up. Oftentimes in the clean up, you follow solid phase extraction based on similar to what Gary talked about in the GC. But one method is the quick, efficient, cheap, effective, rugged, safe. These are the cinnamon, the abbreviation, but you do not have to learn it by heart. But it's good to know. So you extract based on the chemical characteristics using solid phase either extraction or micro extraction depending on the size. And you use accelerated solid extraction to purify and concentrate. And then chromatography, mass spectrometry, often takes mass spectrometry, and immunoassays or immunoassays. Okay, pesticides. So we have so many registered pesticides. So to be a registered pesticide, that means it has been proven that it is acceptable at a certain level to be present in the crop, so that it doesn't cause harm to the consumer. So any pesticide that needs to be used should be registered with the government, and then the tolerance level identified before application. And most commonly we use the multi-residue analysis, where you can look at multiple pesticides at the same time, the same extraction, similar assay, GC or HPLC. Single residue, you can use immunoassays, and you can use unique extractions and use GC or HPLC. Again, this is only used if you are looking to register a new pesticide and you need to identify an tolerance action level. Thin layer chromatography and enzyme inhibition are methods that are semi-quantitative or qualitative. So here's a quantitative method using GC. It's mostly used, GC, because pesticides, most of them are thermally stable and volatile. So you can use different colors based on the pesticides, and then different textures as well based on the pesticides we're looking for. You can use internal standards to enhance the sample preparation, reduce errors, and if you're looking to quantitate, you obviously need external standards. HPLC is used with the polar pesticides and that are non-volatile and non-thermally stable. Again, the choice of column depending on the analyte itself, and detector usually mostly is UV, fluorescence is used, and in many cases you use MS to confirm the identity of your pesticide. And the MS usually is MS-MS, that means you have MS in tandem to get more fragmentation, reduce the noise, and be able to compare your sample to your standard by doing tandem MS. Pesticides can also be determined, or their presence identified, by ELISA using the antibodies. And because they're small, so if I ask you to give me an example of a competitive ELISA, use of a comparative ELISA, it would be a pesticide. Pesticide, mycotoxin, anything small would be a good example for comparative ELISA. You can do screening before doing elaborate LC-MS or GC-MS. You can do thin layer chromatography, and it's very easy to determine pesticides. Usually pesticides inhibit a very unique enzyme in pests, the cholinesterases. So what you would do is you would get an extract from your sample, you run it on thin layer chromatography, then you spray the whole plate. You spray it with an enzyme, with this enzyme, the cholinesterase, and then you incubate it with a substrate. Then what you see is the color, right? So you have the enzyme, you incubate with the substrate, you can color on all of that plate except for where you have pesticide. Because the pesticide is going to inhibit that enzyme from functioning. Then you would know, okay, I have different pesticides in there. In order to identify what they are, then I can take these samples and do further testing with LCMS or GCMS. So that's kind of an introductory method that you would do for screening before going to elaborate methods. So mycotoxins, so they're secondary metabolites of fungus or molds, and one common one is Aspergillus flavus. And you get different types of toxins. The most common one is aflatoxin and ochratoxins. And some of them are really toxic to a sense that they are not allowable in any level. Others you can tend to have a tolerance level, but a very, very low tolerance level. So ways to detect them, you can always also do a thin layer chromatography, reverse phase HPLC coupled with mass spectrometry, or comparative ELISA to do screening and semi-quantitation. And we can do immunoassays chromatography as well for separation and quantification. Okay, so I'm going to stop at drug residues, and we'll continue on Wednesday. Wednesday, please, we will come 10 minutes early, or after you eat the pizza. As soon as you're done with pizza, we'll try to finish this. And the last topic.
Do we have to come to this class?
Yes. Yeah, I don't have the room reserved for lecture time. Remember, on Wednesday, we're meeting in room 23 in the basement of Food Science and Nutrition.
Did you watch Lincoln Red last night?